here we will import some time series from an electroencephalogram and check its frequency components by means of the Fourier spectrum. The Fourier spectrum is a way of transforming the data from time series such that we can see the frequency contents of the fast, the medium and the slow components. And it will be quantitative for all the it will be quantitative, and it will be determined quantitatively for all the frequency components. So I import some functions that we need, and specifically we are going to import something called FFT, which is short for fast Fourier transform, which is the function that does the Fourier transformation of the data for us. And it comes from Scientific Python or SciPy library. So I activate this, and then there's some code to read in data into a data frame and to extract a NumPy array of data. We have electroencephalogram, of which we take the first two channels, so FP1, FP2 in terms of anatomical locations, and you can see the voltage is displayed in microvolt here. If we check the shape of the data array, then it tells us that we have selected 1280 rows, which corresponds to 5 seconds of recordings from two channels at a sampling rate, which is specified here at 256 recording points per second. Now that we have the data, we want to have a look at what the data looks like. So we import a function to plot the time series, and the function is called plot series. It requires data array as an input, and second argument is the sampling rate. So I activate this function and I call it with plot series, and I provide the data array and the sampling rate as an input, and we can see those two columns that we have displayed here show us a very peculiar form of human electroencephalogram. And very notably in this kind of recording, we see that unlike what you can see in a normal person at normal times, this has a very specific periodic pattern. So there's a repetitive motif in those data that consists of this sharp component, which is referred to as a spike, and then a slow up and down, in this case of the line, but repeated, which is called the wave. So this is a pattern that you record during epileptic seizures of a specific type. That's called an absence seizure in technical terminology. So what we want to do is we want to find out at what frequency is the main component of this EEG, namely the repetition of that motif. You can estimate it visually by saying how many repetitions are there per 5 seconds, and then divide it by 5, and you will get a guess of how many of those components are there per second. And you can see that roughly between second 1 and 2 you have 1, 2, sort of a little bit more than 2 of those motifs repeated. Now that we have seen the data displayed as time series, we want to transform them into the frequency space or frequency domain, as we typically call it. So we do that by creating the Fourier spectrum of the data, which I call data FFT, and I get it from using the function FFT, which we have imported and applied to the data. So in addition to giving it the array that it needs to use to create the Fourier transform, we also need to specify along which axis we want to have that executed. And if I specify the axis with a keyword argument as 0, it means please use the rows as the axis to calculate with. Please use the rows as the axis to calculate along. So 0 means it's the first axis, these are the rows, and if you wanted to calculate it along the columns, you would specify axis as 1. So that will give us the Fourier transform of whatever is in data, so in this case of the 2 time series, and we can check the result by asking the shape of that data FFT, and it's the same as the original data, so we haven't really changed anything. And now comes the point where we want to plot, of course, the result. So this is not quite straightforward, and I'm not going to explain the whole procedure here, but I'll give you the code, and it's also contained in the template that you can download. What you need to do before you can plot it, you need to calculate the frequency and the amplitudes from the spectrum that you have according to the data that you have offered for the Fourier spectrum. So as you can see, I first specify a variable called rows, just taking the number of rows that are in our data array. And then using this knowledge, we have then calculated the frequency content, right? And this is only to get the proper horizontal scale for the plot, the frequency space, so to speak, or the frequency domain. And once we know that, we can plot the amplitudes of the frequencies in that space by calculating them from the output that we obtained from the Fourier transform. And you can see there's a lot that we need to do. We need to take only half of the output because that's actually complex numbers, and the other half is like a mirror image of the original. And then we take the absolute value, so that's the real part of the complex numbers only, nicely summarized here. But the outcome will be that we have the amplitudes as a function of the frequencies, which means we can see for every frequency we will see how large is the contribution of that frequency that taken together generate the signal that we originally provided. So if we have that, then we can say fig x and call subplots as usual, and create our plot using some simple function like plot, and we use on the horizontal axis the frequency, and we plot on the vertical axis the amplitudes. That's it, and suppress any output from matplotlib, and this is what the Fourier spectrums should look like. So what you can see for our sampling rate of 256, and remember that was samples per second, what we get is a Fourier spectrum that contains 128 frequency components. So it's not quite coincidentally half of the sampling rate. And you remember I just said there's this mirror image that we cut off. That's the reason why you have only half the components compared to the sampling rate. So you get 128 frequency components, most of which actually don't show anything as far as we can tell visually from this plot. Everything above, say, 20, and this is hertz, so cycles per second on the horizontal axis. Everything above 20 is basically useless. There's nothing in there in this specific signal that we provided. So everything that happens is between 0 and 20 hertz, and we can get this section highlighted if we use a specific command for matplotlib, a specific function. So I just copy and paste the code. Let's just copy the plot, and do another plot below here which uses the same instructions as before, but in addition we specify that we only want to see the first 20 Hertz. So we do that by specifying set x lim, which is the limits of the horizontal axis or x-axis. And it's very easy. We specify the lower and the upper boundary as two numbers. So if we remember, our original plot started at 0, we start at 0 here, and instead of plotting everything, we just go up to 20 in the zoom of that original plot. So I make that slightly bigger, and the zoom with x limits between 0 and 20 shows us that this signal has a frequency component, one dominant frequency component, as we can see, namely the amplitude, which is on the vertical axis, is very high for a component at, and we have to read that as Hertz, on the order of 2.6 or whatever it is, or 2.7 Hertz. Or if you like, we can also zoom a little bit more and just look at components up to 10, and then we can see it, well, that would be 3 somewhere here, so it's closer to 3 than I estimated before. So at that frequency component we have the highest amplitude, and that means this is the major frequency contained in our original signal. Let's go back to the time series. So 3 Hertz or 3 cycles per second means that is the repetition frequency of the motive that we can find in that signal here.